Okay, so we were talking about exceptions in the last lecture. I'm kind of covering the exception material in two parts, kind of some of the more basic stuff to begin with, is what we're doing now. We'll come back and revisit exceptions a little bit later in the course, but I just want to kind of give enough that at least you won't have any problems using exceptions at a more basic level, which is used in some of the assignments. So the next thing I need to talk about is the noexcept operator. So this is different from the noexcept specifier that we talked about before. So when you're declaring a function, you can use a noexcept to signal whether or not the function throws exceptions or may throw exceptions or is guaranteed not to. There's also a noexcept operator, just to make things more confusing. I mean, most likely the reason that they did this is that you don't want to kind of use too many identifiers or too many keywords in the language, because every keyword you use is something that could conflict with variables that are already being used in programs. So depending on how you use noexcept, it might mean one thing or something completely different. What we're talking about here is the noexcept operator. So this is an operator that essentially tells you whether something about the noexceptedness of some expression that you might want to evaluate. So essentially it takes an expression, so it's an operator that takes an expression, so you have noexcept and then in parentheses some kind of expression that evaluates to a bool, and it indicates whether or not it evaluates to an expression which is true or false, which indicates whether or not the expression when you evaluate it could potentially throw an exception. So I might have misspoke, but the operand itself is not a Boolean, but the value that's returned by the operator is a Boolean. And you can basically give it any expression. It doesn't actually evaluate the expression. It just said, if I did evaluate it, what could I expect in terms of things throwing exceptions or not? And I'll maybe elaborate what's meant by this point here as we go through an example. But when it's making the determination of whether something can throw an exception or not, it's only using the noexcept properties that you specified with the noexcept specifier for functions. So even if something categorically never throws an exception, but it doesn't promise not to, as far as what this operator is concerned, it will say it could throw. So it looks at the actual declaration of the function, whether it has a noexcept in it or not. Anyway, so I have a code example down below here where I'm using various different combinations of the noexcept operator. So here, for example, we're saying noexcept 1 plus 1. So again, noexcept, you give it some expression that you want to evaluate, and you want to know, could that throw exceptions? Well, adding the integer 1 to int 1 to int 1, this better not throw any exceptions, otherwise something's really hosed with the compiler, or something's hosed somewhere. So this would evaluate to true, for example. And I'm just using static asserts to show, yes, in fact, these things really do evaluate to what is claimed on the slide. Here I have a situation where I have this function up above that's being called. So this memAlloc, which presumably does some kind of memory allocation, maybe allocating a certain size, a block of certain size in memory, and maybe returning to the first byte in it or something like that. So I'm calling memAlloc. I want to say, if I call memAlloc, could it potentially throw an exception? So this is essentially what I'm testing here. And it's returning false. noexcept is returning false, meaning if I evaluate this expression, it could throw an exception. It's not necessarily noexcept. Notice here that I can do really, well, actually, no, this is not a good example for that. I'll get to this in a moment. It doesn't actually evaluate the expression as the noexcept operator. So this becomes important if I'm trying to do something like this, because what I'm doing in this expression here that I'm plugging into noexcept operator, this has some very dubious looking code in it. I'm taking a null pointer to an int, and I'm dereferencing it, right? This is bad news. So if the compiler actually evaluated this expression to figure out whether it's noexcept or not, you'd be in big trouble. But if you're guaranteed that these expressions will not ever be evaluated, it won't actually call the functions in them. All it does is it looks at the types, because it can tell, depending on whether, for example, the function that's involved here, depending on whether the function increment is guaranteed not to throw exceptions or it doesn't make such a promise, it can figure out whether something might throw an exception. So it's a completely compile time thing. No code is going to be called, and it won't actually evaluate the expression beyond just trying to figure out whether the expression could yield something that's noexcept or not. And we can also, so yeah, I guess this is the more interesting of the two lines. So if we look at increment the way it's specified up above here, it's specified as being noexcept. So we know that this shouldn't ever throw exceptions no matter how we invoke it. So this evaluates to true, meaning, in fact, when I evaluate this expression here, this won't result in an exception being thrown. Although if I do this at runtime, it would result in undefined behavior because I'm dereferencing a null pointer. But that's okay. You can do weird stuff like that in these expressions because they're not actually evaluated. And then I guess the last example I want to consider is this one down here on line 18. If we go back up above here and look at how no does not throw this function is defined, you notice that there is no noexcept specifier that's specified, I guess it would be here. So what's going on here in terms of the contract that this particular function is making with the rest of the world, it's not promising not to throw exceptions. But clearly, if we look at the definition, because the definition of the function is right here, like categorically, we can say it's not going to ever throw an exception, like it doesn't do anything. So it's not going to throw any exceptions. But it doesn't matter, like whether it throws or doesn't throw in reality is irrelevant. Like what matters is what's the promise that's being made by this function. This function does not promise that it won't throw. There's no noexcept here. Therefore, when the compiler evaluates this expression here, it says like, are you guaranteed that this function won't throw exceptions? It says no, false, it could throw. So like it only considers the way that you declared the function. It's irrelevant what the function actually does. And if you think about it more, it would have to do things this way, because you could have situations where you have the function declaration visible, but the definition's in another source code file, another translation unit. When you're compiling this file, the compiler has no idea what that function does. The only thing that's guaranteed to be visible is the declaration of the function. So the only thing that it can use to judge whether an exception might be thrown or not is what's in the declaration. In other words, like for example, whether there's a noexcept here or not. So hopefully that makes some sense. Like if you think about it a little bit more, this is the way it would have to be, because you might say, well, why doesn't it just look at the definition and say, well, it doesn't throw? Well, the definition could be in another file. You could legally write the code that way. The compiler couldn't tell then. A question?
So can you create a function, declare that it is no exception, but then in there, like, say something from the standard library that may throw an exception?
Well, as long as it doesn't throw, you're okay.
Like you can declare it as no exception even if, well, possibly. Because like, I might write...
Basically, you're asking, like, can you throw a function that's not noexcept from within a function that is noexcept? I think that's what you're asking.
I'm like...
Or maybe I'm misunderstanding.
I write a function and I think it's not going to throw an exception, so I write no except in there. But then maybe some library function I'm calling in there actually is not safe and can throw.
Because again, when you make a function noexcept, it's not saying that internally the function won't throw exceptions. What it's saying is that the external user will never see an exception being thrown out of the function. In other words, it's all about the API, essentially. Like, what's the visible behavior outside to people who call you? When you say noexcept, what you're saying is, hey, anyone who calls me, I promise you will never see an exception come out of me. But inside, there could be all kinds of gross stuff going on, exceptions thrown all over the place, but like you catch them before they ever propagate out. You catch them, handle them before they ever propagate out of the function.
Is it possible if I can make a mistake, though?
Well, sure, but there's lots of mistakes you could make, and that could be one mistake you could make where accidentally an exception propagates out of a function because you don't catch it, and then it's noexcept, and then you end up terminating the program.
So if it does throw, it's going to terminate the program?
If you throw it, if you emit, maybe to be kind of very precise in my wording, if you emit an exception, like in other words, let it come out of the function. If you emit an exception from a function which is noexcept, the language standard requires that your program be terminated by the runtime, like the runtime environment. So you don't ever want to throw an exception from, like actually let an exception propagate out of a function that's noexcept. It's just like with const, like the compiler takes it seriously and enforces it. Although in this case, the enforcement is at runtime, but essentially the compiler generates the code or in conjunction with the library that makes sure that you don't do these things. Any other questions? Okay. So a little bit more about the noexcept operator, maybe to show like a situation where maybe you might use it. So essentially where the noexcept operator is useful is you're trying to specify the noexcept properties of a function, like a declaration for a function. You want to say noexcept, but like sometimes it may always, like it could always have the possibility of throwing. In other cases, maybe in certain circumstances, it's never going to throw categorically. And typically where this is going to be an issue is when you have template code. Like we have some template code, for example, we have a template function that's performing some kind of addition operation. And then the subtlety here is that in order to implement this function, well, it's a very simple function. We're just using the addition operation, which is presumably overloaded for the type T. So the type T, whatever it is, it's getting plugged in here. Presumably it overloads the binary addition operator so that we can legally write x plus y and have it make sense. But it's possible that maybe x plus y for some numeric types could actually throw an exception. The situation realistic really where this could happen is maybe x and y are like some kind of arbitrary precision arithmetic types where they can represent like any value exactly, and then when you do arithmetic, it essentially adds more and more decimal places to the number. Essentially the size of the type then can grow, so there's going to be some memory allocation associated with that type. And anytime you're doing memory allocation, you can run out of memory. So you could run into sort of exceptional circumstances, and maybe the way the code signals this is it signals this by throwing an exception. So here I just like have two different integer types, one which is like a 256-bit integer, and then this thing called big int, which is like a kind of flexible length integer. It can be however many digits you need to represent it, however big a number you happen to have. And maybe I want to have, I mean, this is a very contrived example, probably in practice you wouldn't write something quite like this, but at least it illustrates the point anyway. So I want to provide like an add function that can add either one of these types of things in 256 or this big int. And big int would be allocating memory because it keeps growing in the number of digits. When you do more computations, it can represent any arbitrary sized integer. Because of this, it's going to do memory allocation. So because possibly when you're adding these two numbers, that might need to allocate more memory, and that could fail. So you might have a situation where you want this template code to make the promise that, like kind of a more precise promise than just saying, well, there are some types I might plug in for t here that it's going to throw exceptions, so I can't put noexcept in at all because like it might throw. But then I said, well, wait a minute, though, for some types I know that it will never throw. I don't really want to, like in the cases where it won't throw, I really want to say it won't throw. And in cases where it might, then I don't want to say anything. This is where the noexcept operator becomes useful. So what I'm doing is when I declare this function, I'm saying noexcept, but rather than just saying like noexcept true or false, what I'm doing is I'm giving an expression. And what the expression is basically saying is that, like, if I can compute all the things that I need to do in this function such that they don't throw exceptions, then I can guarantee this function won't throw exceptions. And in this particular case, well, the obvious thing is that I need to be able to add x and y without throwing exceptions. So I'm basically saying like this function doesn't throw exceptions as long as adding x plus y doesn't throw exceptions and the type t is move constructible without throwing an exception. In other words, you can construct the object without throwing an exception. I was thinking about this a little bit more this morning. I'm not sure if this is required in C++ 17. For legacy reasons, it might be needed. I think, well, if the copy is elided here, then I don't think you need the guarantee about the move constructible either. I mean, this is basically because this is returning by value. So if there's no copy of elision taking place, then you need to propagate the return value out of the function. That's a copy or move. Well, in this case, it would be a move because it's not an LVAT expression. This could throw potentially, which is deemed as part of the code that's running for the function that's being called. Anyway, I don't want to get too hung up on this, but I think that maybe this is not required now because I think that the way this code is structured, probably this is going to elide the copy. But anyway, the more important thing is maybe this part here, the x plus y, because that's kind of more obvious. Adding an x plus y, we need to guarantee that that won't throw exceptions. And yes, if you really want to be precise about this, and this gets to be like a longer function, you can end up with quite a long expression for the noexcept operator. Any questions? Yeah?
So is noexcept x plus y saying, does the function that like operator plus, does that not throw exceptions? Or what are you saying in that noexcept x plus y is?
Yeah, so this noexcept here is the noexcept specifier for the function. Yeah. This noexcept here is the operator. So this is why this one it's taking an expression here. And basically what the compiler does is it says, if I try to evaluate this expression, and at this point when you're using the template, it would know what t is. So like it knows the type of x and y. So it would then know you're trying to invoke the binary addition operator for that type t, which in this case I guess is either int256 or big int, and it would then look and see, is that operator plus defined to be noexcept or not? Okay. And if it is noexcept, then it would say, well, yeah, I can guarantee that this plus won't throw an exception. If it wasn't, then it would say I can't guarantee this, and then this would evaluate to false, saying that it could throw an exception. So like it's all based on how the function is declared, like the thing that's being invoked in the expression that you write. It's irrelevant whether the function actually does or doesn't throw exceptions. It just looks at the noexcept specification for the function for the reasons I mentioned before. Does that make sense? Okay. Any other questions? Yeah?
I'm just still trying to follow that same thing out. So if it did return false from the noexcept x plus y, how does the other noexcept interact with that?
Well, this is just like a normal like logical AND. So like, if this thing doesn't, so this would be true if this doesn't throw exceptions, x plus y. So you're basically saying if x plus y doesn't throw exceptions, and this is a type trait in the standard library. Basically, it evaluates true or false depending on whether or not the type that we're plugging in here can be constructed by a move without throwing an exception. In other words, what it's saying is like, if I did a move, the thing that gets called, which either be a move constructor or copy constructor if there is no move constructor, does the thing that eventually gets called, does it make the promise that it doesn't throw exceptions? In other words, is that move or copy constructor noexcept is what this is testing. But again, as I was thinking about this morning, I'm not sure whether this is required because I'm claiming that all of this is for C++ 17. I think that this might not be required here, because if the copy is elided, then there is no move needed. Anyway, I'll think more about this, but it's not a really big deal. The main thing really I wanted to illustrate was the first noexcept part here. Yeah?
So when we do noexcept here, you said it only actually looks at the type. So it only looks like the declaration type to make sure that it's noexcept.
Yeah, like it's looking at the declaration of the function.
So when we pass these parameters, all it's doing is it's trying to figure out which function is going to be called, so that you can have a look at that one. So, but it doesn't actually do any sort of evaluation. So
yeah, this is why it doesesn't need to evaluate things. Like this is another side effect of, or like another benefit of making the noexcept operator based on the declaration of the function, whether it's noexcept or not, rather than what the function actually does. And then this is another advantage of doing things this way, is that there's no need to actually call anything, because you can statically, just by looking at the expression and look at what functions are called, figure out whether it is possible an exception might be thrown or not.
So
if you made it depend on what the function actually did, then you would have no way but to evaluate the expression.
If the parameters are like something that's auto and we don't know what it actually is until maybe runtime, does it have to check?
Well, no, auto things, like when you deduce types, they always have to be deduced at compile time, because like the types of things is like a static property of the program. So you would run into problems if things work the way that you're talking about.
So there's no case where you don't know what the type is when you're calling it.
At compile time, the compiler, if you say auto, the compiler, what you're doing is saying, figure it out for me, but it's always figure it out for me at compile time, right? Because the compiler, when it's compiling the code, if it wants to generate any code, it's going to have to figure out what types are involved. Otherwise, it might even know what functions are going to be called and so on. So auto is like a compile time thing, yeah. Any other questions? Okay, so that brings us to the end of sort of exceptions part one. We'll come back to a little more complicated stuff a little bit later in the course. What I want to do next is talk about some things that pertain to computer arithmetic. In particular, what I want to talk about is something called interval arithmetic. It's a technique that has quite a few different applications. The essential idea behind interval arithmetic, like first of all, floating point arithmetic, a really important thing to understand is that when you use floating point arithmetic, essentially every result that you compute is wrong. Well, with some like exceptions that I don't really talk about. If you just randomly pick two numbers, floating point numbers to add, the chance of you getting the exact answer is essentially close to zero. So in other words, floating point arithmetic fundamentally involves round-off error. And if you stop and think about this, this should be sort of deeply troubling to you. You know, if you're writing a calculus exam and every answer you have on the exam is wrong, you're probably not going to fare very well, right? But if you're doing real arithmetic on computers, it's like essentially every answer you compute is wrong because you have round-off error. So if it doesn't deeply trouble you about this and you go like, isn't this going to cause problems? I mean, every answer you compute is wrong. Well, yeah, this can be like a massive problem in certain application areas. In some areas, it's not a big deal because as long as you're careful, the round-off error might not be too large. So you get the wrong answer, yeah, but it's close enough to the right answer, it doesn't cause problems. Although, even in some numerical applications, if you're not careful, the round-off error can get huge, like 10 to the 200. Like it's not, round-off error is always small. It can get really, really big if you're not careful in certain situations. But there's some applications where you can't accept any error whatsoever. Like maybe you're, I don't know, like just this kind of very synthetic example, not the best one, but at least it's something that's easy to understand. You're designing aircraft or something, and you're doing some calculation to figure out, will it fall out of the sky or not? You probably want to be sure the answer you get is, that if you get no, you really are sure that the answer is correctly no. It really won't fall out of the sky. You don't want it to say yes, but it wasn't quite the right answer because of round-off error that was used to calculate it. So there are certain situations where it's absolutely critical that you get the right answer. Typically, the sort of situation where this arises is maybe you're using the result as a predicate in your code. So you're basically saying, based on this computation, like the result that I get, I have some like if involving that result. And if it's greater than this, do this, else this, or something. Or actually, the more troublesome thing is maybe if x equals this, do this, else do this. And then the problem is because of round-off error, it changes the path in the code that you'd hope that it would take because you get the wrong answer. Then if you say if x equals something, well, you're not really comparing to the right thing because you got the wrong answer to begin with. So it becomes a really big deal when you start having round-off error in certain sort of applications. So interval arithmetic is one way to sort of combat this, or this sort of problem, where what we do is we no longer have values that correspond to a single value, like a single real number. Instead, what we do is all of the computation we're doing involves intervals. Aside from dealing with like round-off error and stuff like this, I mean, there may be some applications where fundamentally there's uncertainty in the numbers that you have that you're feeding into your program. And maybe just rather than saying, oh, forget about all the uncertainty, I'm just going to give it a value. You know, it's 5, but I don't really know if it's 5. It could be like 4.9 or 5.1. So there are some situations, like any time in science, if you're making measurements, there's always measurement error. There's always uncertainty. You say something's 5 meters long, but it's never going to be exactly 5 meters. There's some, you know, depending on how accurately you measure, you might be within a millimeter or micrometer, but it's never going to be exact. So in situations like this, even if maybe you kind of ignore the fact that round-off error may later be introduced by computation you're doing, sometimes fundamentally the data you have, it doesn't really make sense to assign a particular number to it, because you know from the get-go that the number is not exact. So why not reflect that in the computation you're doing? And the actual input to the program would be a range, like this value, you know, the length of this thing, I'm not sure it's around 5 meters, but I know that my accuracy of measurement, I can guarantee it's within like 4.9, 5.1 meters, something like that. So this is kind of the idea behind interval arithmetic. So everything is represented as intervals, the values that we're doing computation with, and then we define some kind of meaningful way to add intervals, subtract intervals, and, you know, do the basic arithmetic operations on intervals. Is there anything else I want to say here? I guess that covers it. So some sort of applications of interval arithmetic, there's lots of them. I mean, one big area might be like the numerical algorithms where maybe things might be very ill-conditioned. Like when you start dealing with computations where typically the thing that gets you into trouble in terms of big round-off errors, you start having very large magnitude numbers and very small magnitude numbers that you're doing operations on. Like add a huge number to a really small number. Basically what will happen, you get the big number for the answer because the other number becomes a round-off error in the computation. So you can get and that can kind of accumulate over time potentially. There's some other applications, and the one that we're going to look at in some detail is what I call robust geometric predicates. So basically in geometry processing. So for example, if you're doing games and stuff like this, or anything that involves geometry in 3D, for example, or even 2D or 3D, whatever, you have to sometimes answer questions like you have a line and you have a point and you want to know, is the point on the left side of the line or the right side of the line, or is it actually on the line, things like this. So these are basic geometric predicates where you're testing for like a small number of outcomes, like it's left of, it's right of, or it's on, or something like that, or above or below or on, these sorts of things. And typically the way predicates are used just in general in code, they're used to make decisions in your code, right? So if you have something that's doing computation and then making a decision based on the computation, like it's basically evaluating some predicate saying like, is this true or not, for example, and due to round-off error, you give the wrong answer, the consequence of this is usually a disaster, right? Because the reason that you wrote an if statement in your code, like if this predicate is true, do this, else do this. The reason that you wrote the if, presumably, is because you care that if that thing is true, you do one thing, and in the other case, you do something different. So if the predicate's wrong, essentially what happens is it reverses what you want to have happen. The thing that you wanted to have happen in true case become what's happened in the false case and vice versa, which is probably going to break your code, right? Because the reason you had the if statement is you probably cared which of those things actually executes. So just generally speaking, if you're evaluating predicates that are based on floating point computation results, or arithmetic, just basically real number arithmetic results, you probably care a lot about whether the results, if there's error in those results, because it could cause the result of the predicate to be wrong. And in geometry processing, this is a really big problem. There's lots of things where the algorithms probably would not work if the predicates give the wrong answer. But because of round-off error, they can very easily give the wrong answer. And then I've listed a few other application areas, like things like, if you're into ray tracing, then some steps in algorithms and ray tracing, this can become problematic. Also, maybe things like if you're trying to do a mathematical proof by computer and you want to be able to bound the error in what you're doing, then interval arithmetic is useful too. Essentially, any application where you need to bound the error, you need to be able to say with certainty the true answer lies between this value and this value, and you want to be absolutely certain about this. Interval arithmetic is very useful for this. So before we get into sort of the practical implementation aspects of things, I just want to talk about things kind of a more abstract mathematical point of view. So let's just forget about like floating point numbers and just suppose that we can exactly represent all real numbers. And we want to introduce some kind of notion of interval arithmetic for real numbers. Then basically what we do is the actual values that go into the computations we do, like adding, subtracting, multiplying, dividing, so on, they're all intervals. And what I mean by an interval is you just have a range of numbers, between A1 and A2, where these are real numbers, including both A1 and A2. So like it's a closed interval at each end. And you're basically representing a whole range of real numbers using this. And then we can define like addition, subtraction, multiplication, and division. And the way that would probably make the most sense and what's typically done is, for example, the way we would define the addition of the interval A and the interval B is we would say you take every element from the interval A, add it to every possible element from the interval B, and generate a whole new set of numbers. And it turns out this is always going to be a range of consecutive real numbers. And we can define this result to be A plus B. And we can do a similar thing for minus and also multiplication and division as well. Division becomes a little bit more tricky because we could divide by 0. And if we allow division by 0, then this makes like a lot of things more complicated. We can still handle it, but it makes things a lot more unappealing. So more gross anyway to implement. And for some applications, it's not necessary. For the particular applications that we're going to consider in this course, we don't need to do division. I mean, some applications you might need to do division as well, and then you may have to worry about this because maybe you might divide by 0. But if we don't divide by 0, then we can, in a very kind of relatively straightforward way, we can define division without too many complications. So these all kind of follow a similar pattern. Again, you just take each element out of the set A, each element out of the set B, and perform that operation, whether it be addition, multiplication, division, subtraction, and you generate a new set. And this is always going to give you a range of integers, and this is the result of the interval operation that we're performing. And to be a little bit more concrete, for example, if you have an interval A, which is corresponding to like A1 to A2, and an interval B, which corresponds to B1 to B2, and we add these, the result is always going to lie in the range with A1 plus B1 is the lower limit, and A2 plus B2 is the upper limit. And we can do similar things for subtraction. Subtraction, the only tricky thing about subtraction is because we have inequalities involved, right? Because the notion of, like what this notation is saying is it's saying that this represents a number that's greater or equal to B1 and less than equal to B2. And then if we're taking the negative, essentially what happens is we get negative signs and inequalities. And remember, when you multiply by negative, then you have to flip around the inequalities. So because of this, although this might be initially counter to your intuition, if you think about it, it sort of makes sense. The thing you'll notice here is when we take the negative B1, B2, it's not just that the limits get multiplied by -1, but they also flip. Now we have B2 is the lower limit and B1 is the upper limit. But if you kind of trace through, I mean, basically where that comes from is from just kind of messing around with the inequalities, because you have a negative sign and inequality, it will reverse the sense of like greater than and less than. And this is the reason why you get this kind of flipping around. And once we can negate a number, then we can easily subtract. This subtracting is just adding the negative. So that just comes from, this just comes from the two formulas up above. And you'll notice that the thing we're subtracting and the B2 and B1 are kind of swapped from what you might initially think they are if you don't really think about what's going on in terms of the math. And then we can also define multiplication and division as well. I'm not going to try to go through and like prove any of the results of these formulas. It's not really that interesting or helpful to go through. But you can show that, for example, multiplying the interval A1, A2 and B1, B2, it gives you a result which corresponds to some stuff involving minimums and maximums of various combinations of things. And similarly for division, we have a similar kind of thing. But again, we're assuming that we can't divide by 0. So in other words, the interval here at B, we're assuming that the interval B1 to B2, it can't include 0. If it can, then things become more complicated. And I'm not going to talk about that in this course. The slides actually cover it, but it gets a little bit messy, and it's not really, I'm going to not briefly comment on these. But these slides, if you want to look at them, they kind of talk about some of the issues that can arise if you allow division by 0. So kind of putting that to the side then, so this is kind of an abstract introduction to interval arithmetic, like from a mathematician point of view. Now what I want to look at is how do we translate this into actual algorithms when we're implementing interval arithmetic on the computer. So in the case of the computer, we're using floating point arithmetic because there is no processor comes with a built-in real type. Like it's real in the sense that you can represent any number exactly, because this would lead to like really immensely complex hardware. So basically what we're going to be using is floating point arithmetic to implement this. So we follow a similar pattern. We represent represent numbers using intervals. The only difference is now these endpoints of the intervals are not arbitrary real numbers, they're specifically floating point values. And the reason why it's important to make a distinction is obviously there are some real numbers we cannot represent. Like in other words, this F here is a subset of the real numbers. There are an infinite number of real numbers that we cannot represent exactly inside the computer. But it turns out this is not a big barrier, at least for most situations in practice. So basically we again have endpoints of the interval, and they represent the range just like what we had before. The only difference is our endpoints are now machine representable values, actual floating point values, real numbers that can be represented in floating point. And the basic idea is whenever we perform, anytime that we're performing, like the thing that leads to round off error is when you do a computation, most likely the answer you get can't be represented by the computer, because there's an infinite number of real numbers that can't be represented exactly, and only a finite number that can. So percentage-wise, there's infinitely many more that are going to incur round off error compared to ones that won't. So kind of in a statistical sense, most likely you're going to encounter round off error, which means that what we do is we take the answer that we can't represent and we represent it with the closest value, closest in some sense by rounding. So this is kind of the problem that we're trying to get around with interval arithmetic, is the fact that we have this round off error being introduced, and we don't really have any way to know how big or small it is. We can't really bound the error. But with intervals, we can, because we can say with certainty the answer lies in some particular range. Any modern processor allows for control over the rounding mode. So when you're performing like floating point operations, you can, for example, say I want to round the result that's computed to the nearest machine representable value, or I round towards 0, or I round upwards, or I round downwards. So like rounding towards 0 is just throwing away the fractional part, which is basically truncating the number, or rounding upwards, rounding towards positive infinity, rounding downwards, rounding towards negative infinity. So this would be like this kind of like the ceiling function, taking the ceiling of the result. This would be like taking the floor of the result. And you have basically special instructions typically on the processor where you can change the rounding mode that's used. And the basic idea behind using floating point arithmetic in conjunction with interval arithmetic is that we're going to compute each result twice. Once saying like, what's the lowest possible answer I can get? What's the highest possible answer I can get? And basically bounding the true result within upper and lower bounds that correspond to the interval. So whenever we perform any sort of arithmetic operation with interval arithmetic, we want to make sure that we continue to like the interval that we produce is the result of whatever operation we're doing, whether it be addition or subtraction and so on. We want to make sure that the interval we produce contains the correct answer. So although we maybe can't represent the true answer because it might not even be representable like in the floating point implementation that is used by the processor, we can make sure that the range that we specify for the result includes the true value. So this is the basic idea behind interval arithmetic. So typically what we do is we'll compute each operation, whether it be addition, subtraction, multiplication, division. We do it twice. Once rounding downwards, so we force any error to accumulate sort of in a downward direction. So effectively what we're going to do is we're going to lower bound what the correct answer could be. The answer that we get for the lower bound, we're guaranteed the true answer is always greater than or equal to the lower bound we compute, because we're always rounding down. So we're kind of being pessimistic in the negative direction. So the answer we get would be less than or equal to the true answer. And then we do a similar computation, but with the rounding in the opposite direction, rounding towards positive infinity. So effectively what's going to happen here is we're going to overestimate, like specify a value for the answer which is greater than what the real answer is, or it could be equal if we're really lucky and there's no rounding error. And by doing things in this way, we can ensure that the results that are produced by interval arithmetic, they give us, like the true answer will lie in the range that's specified by the interval result that's produced by the interval operation that we do. So this is why interval arithmetic can be very useful, is because we always know that the true answer lies within a certain range. If we did just stuff with regular floating point arithmetic, we get an answer and all we can say is, well, here's some answer. We don't have any idea how big the round off error is. Maybe it's very accurate. Maybe it's out by 10 to the 200. We don't really know. But whereas with interval arithmetic, we know the true answer lies within the interval. So if the interval is not too big, and this could be a problem, I mean, maybe the interval is massive, like it covers a range of 100 billion, then in that case, there's a lot of uncertainty. But in a lot of cases, the range might be relatively small. So we can say, well, the true answer is between 1.5 and 1.6 with 100% certainty. And then we can say, well, it's not too far off for our particular application. So the next few slides, they just kind of give you the formulas. And again, I'm not going to go into the derivation of these things. It's not really that, I don't think it's not a very good way to spend the time in this course. But I need to explain a little bit about the notation here. So essentially what this is giving is the formulas that you use for calculating the endpoints of the intervals, like the results for different arithmetic operations like addition, subtraction, and so on with intervals. And the notation here, this upside down triangle means like do addition but rounding down. And then the triangle that's sort of pointing in the upward direction means like do adding but rounding up. So effectively what we're doing here is we're doing like all the same formulas we had on the previous slide for kind of the abstract mathematical case. But what we're doing is we're choosing the rounding mode to be such that we either underestimate the true answer or we overestimate the true answer. And we calculate an underestimate and an overestimate, and then the true answer must lie in that range, and that becomes our interval. This is effectively what we're doing. And division becomes a little bit more ugly in the case where we allow division by 0. This one excludes the possibility that we're dividing by 0. There are some slides, if you're really interested, you can look, and there's like, basically this goes on for several slides. Like you can't fit it all on one slide anymore. This is the case where we allow division by 0 to happen, and then you have like a lot more cases, as you can see. But I'm not going to go into any of that in detail. But it makes things a little bit more ugly if you can divide by 0, but for the purposes of this course, we don't need to worry about that because our application doesn't require that. The other thing I need to talk about is, in addition to like the basic arithmetic operations like plus, minus, multiply, divide, we also need to probably have things like relational operators, so we can say like, is this number bigger than this number, like greater than, less than, things like that, because otherwise it's difficult to make decisions in the code. But this is where we get into a little bit of like some problems compared to just like standard real arithmetic or floating point arithmetic, which is that we can get into kind of weird situations. Like, so suppose we have like two intervals, one represented by x and one represented by y. Actually, sorry, two intervals here, a1, a2, and b1, b2. And then we have some relational operator. This circle here is a placeholder for like greater than or less than or equal or less than or equal or something like that. And then we want to attach some kind of meaning to this relational operator. We can kind of run into some problems. I mean, to begin with, things are kind of okay. So we say, well, if this condition, so suppose like this circle means greater than, so we're trying to test if something is greater than, we could say, well, we'll define this expression to be true if for every possible x that we can choose in the first interval and every possible y we can choose in the second interval, we always have that x is greater than y. So in other words, no matter what thing I choose from the first interval and what thing I choose from the second interval, it's always true that one is like greater than the other. Then I could just say, okay, the result of this operation is true. And then kind of conversely, if it's true that no matter which value I choose from the first interval and what value I choose from the second interval, it's always true that this relationship is not true, it's always violated, then I could say that this evaluates to false. This would be like a very kind of reasonable way to define things. But unlike the case of regular floating point arithmetic, you also have this other weird situation that can arise, which is that maybe depending on what particular value I choose in this range, a1 to a2, and depending on what particular value I choose from this range, maybe I can make this relational operator true in some cases and not true in other cases. In other words, you can't really categorically say the result of this expression is true or false because it depends on information we don't really know. Depending on what value in the particular range is involved, you pick, you could get an answer of true or false. In this case, this yields what we call an indeterminate result. In other words, we can't really say whether something is greater or less than because it depends on what particular values we're talking about in those ranges. So to give some more concrete examples, like suppose we have the interval 0, 1, and we're checking to see if it's less than or equal to 1, 2. No matter how I choose values from this range here, anywhere between 0 and 1, and no matter how I choose values from this range, I can never make this condition not true. For example, 0 is less than 1, or like 1 is less than or equal to 1. No matter how I choose them, the condition is always true. So in this case, you would, at least for any reasonable way to define like less than or equal for interval arithmetic, this would evaluate to true. And then for similar reasons, this would always evaluate to false. No matter how I choose a number in this range, for example, if I choose 0, and no matter how I choose a value in this range, so for example, I choose -2, it's always the case that it's never the case that this value is less than or equal to this value. In other words, this condition is categorically always false. But where you run into some kind of trickiness is, well, what happens if I do something like this? I have the interval 0, 2, and I say, is it less than 1, 3? Well, it depends on what particular value I choose from each of these intervals. I guess if I chose, for example, if I chose 0 and 1, then 0 is less than or equal to 1. So if I choose 0 from the first interval, 1 from the second interval, this would be true. But if, for example, I could also choose 2 from this first interval and then 1 from this interval, but 2 is not less than or equal to 1. So you get into this kind of dilemma that depending on what particular value you choose from each of these intervals, you could get different answers in terms of what the relationship is between them with respect to like greater than, less than, and various other relational operators. And like another problematic example would be something like this. You're testing to see whether 0, 1 is equal to 0, 0. Well, 0, 1 includes 0, so I could choose 0 out of this interval, and 0 clearly is equal to 0. But also, like, the value could be equal to 1 as well, or anything in between 0 and 1. But any value between 0 and 1 that excludes 0 would not be equal to 0. So we also have this problem that it's not really entirely clear what we should define this to be. So what we do is we just make it indeterminate and say we don't know. And we just hope that in our applications that either we don't hit this situation that frequently, or at least if we do hit this indeterminate case, it turns out that there's some other way to address the problem, this kind of ambiguity. And typically, maybe the way that you would deal with this in maybe a C++ interface that you're implementing would be, maybe you would throw an exception in this case. Like, you would just want the user to write less than and greater than, just in the way you normally would. But in the case where the result is indeterminate, it throws an exception, and then we basically would have to catch the exception, and that would be a signal to you that some of the relational operators that you're trying to use, the result couldn't be determined, which is basically saying, whatever you're trying to determine based on the interval arithmetic that you're doing, it can't be determined, at least not with 100% certainty. Any questions about this? So, like, you can apply this basically to any of the relational operators.
So in the interval arithmetic, where like subtract or add or something, where you do it on bounds, and then you say new result is bounded, those things that you're performing operations on, those also require interval arithmetic, so it's kind of recursive to some.
There isn't any recursion involved. Like, when you're doing the interval arithmetic, like if you're adding to, like, you have two intervals and you want to add them, you're basically just using the formulas that we talked about. There's not like a recursion where somehow during that computation you then need to do additional interval arithmetic. Like, if that were the case, like, this just wouldn't work, because you'd be in an infinite recursion then.
So you just add the numbers wrong, like from the bounds, and then, because that will have error as well, right? Like when
well, this is why it becomes very important to correctly exploit the rounding modes on the processor. Like, if the processor didn't have rounding modes, then you couldn't really make this work. So the basic idea, maybe if I use addition as an example, if we kind of ignore round off here and so on, hopefully it's somewhat clear that if I added like an interval, like a number between A1 and A2, and I add it to like an interval B1, B2, hopefully it makes sense that like the lowest possible answer I could get would be A1 plus B1. And the largest possible answer I could ever get out of this would be A2 plus B2. Like, the smallest number I could get would be choosing the smallest number in this range and adding it to the smaller number in this range. And similarly, the biggest answer I could get would be taking the biggest answer in this range and then adding it to the biggest answer in this range. So this is where this comes from. And what we want to try to do, when we go to the floating point world, then the additional complication is, well, all the computations that we're doing, we can't rely on them giving us the correct answer because of round off error. So what we do is we say, when we compute this, like, this would all be okay as long as this, like, the key thing is this interval here has to include the true answer, like the correct answer. So if we made this interval a little bit wider, like a little bit bigger than the kind of the ideal one that you would get if you didn't use floating point and you use all exact arithmetic, if we make it a little bit bigger, it would still be okay. In other words, if I take the ideal result of A1 plus B1 and I make it a little bit less than A1 plus B1, we're still okay because this interval still includes the true correct answer in the range that's specified by the interval. And the thing is, well, how would we achieve this? If we know that the result might not be exact, but we want to kind of not have the range like become really much bigger than it needs to be, how can we accomplish this? So what we do is we say, let's round, when we compute the A1 plus B1, let's round it down. So what that means is if the result is exactly representable and there is no round off error, in that really lucky case, it will just make it exactly the same as the true theoretical result. But in the case that it's not machine representable, the result that we get, which will statistically be most of the time, what will happen is we round down, which is saying to the processor, when you calculate this value, give me the closest answer that I can represent that's strictly less than or equal to that result. So this is the reason why we're rounding down here. And similarly, this is why we round up here. So here we're going to potentially slightly overestimate the true answer for the upper end. But the rounding down and rounding up, because we're choosing rounding down for the lower bound and rounding up for the upper bound, if we swap them, then we'd have a mess. It wouldn't work. But the way we're doing it, what we're doing is we're taking an interval, which is maybe like this, and we're slightly making it bigger. But the answer is still guaranteed to fall in that range. So this is the basic idea behind what we're doing. Does that help to answer your question? Okay. I think this is where we were. Are there any other questions about up until this point? Okay, so a few more minutes. So let's get into the practical matter then of how do we actually control the rounding modes. So this is, I mean, You could kind of just write the explicit CPU instructions that are used. It'll be like very architecture dependent. Each architecture will have different ways to, special instructions that can be used to change the rounding modes. But we don't really want to do that, because then we get into like, you have to worry about writing assembly code for every architecture you're running on and so on. So there's some standard library functions in the C standard library, not the C++ standard library, that allow you to set the rounding modes. And the particular functions, they're defined, or declarations for the functions are in this header file called CFENV. And these are just some constants that are defined that are used for these various functions. So we can set the rounding mode using this function called FESetRound. And what we do is we pass in an integer which corresponds to one of these 4 values. And what it will do is it will set the rounding mode to that particular mode. So like this corresponds to rounding towards 0. This is to nearest, which is like how we normally do things by hand when we're computing things. Rounding upwards like the ceiling, and then rounding downwards, which is like the floor. And this returns an int because, at least in theory, it could fail. So when you're writing code and you're using this function, you want to make sure it succeeds. I honestly don't know the circumstance under which it would fail. I've never encountered that in practice, but because it could fail, you should at least check and make sure that it doesn't. Mm-hmm.
So when you do this setting, this is like per process, like each process can have its own rounding mode set. Is that how it works?
Yeah, this would be part of the state of the process. So you don't have to worry about, well, there's other processes running on this Linux system that we're using. What happens if they change the rounding mode? So like the state is per process.
But it's not thread safe. So if you want to have like a multi-threaded program with your
I don't believe it. I don't believe it's on a thread basis, because basically all it's going to do, the implementation is probably just going to invoke the particular CPU instruction to set the rounding mode.
Yeah.
And do some additional checking. I'm not sure the exact circumstance under which it can fail. It might be just that they provide this functionality that it could fail, because on some architectures it could, but maybe it's just that on architectures I've used, it never will. Anyway, but yeah. So then you can also check the current rounding mode, because sometimes maybe you just want to know what it is set to. So there's this one, the get round, which returns the current rounding mode. And in order to, if you're going to start writing code that changes the rounding modes, at least theoretically anyway, you should include this pragma in the header, in the file that you're actually going to be messing with the rounding modes. This is not actually implemented, though, I don't think, either in Clang or GCC. So, but you can put it in your code anyway. Pragmas are ignored if they're not supported, so it won't cause your code not to compile. But you might get a warning message saying that this pragma is unsupported or something like that, or maybe it just doesn't say anything at all. Yeah, I think there's an option that you need to specify for GCC, where you can basically tell it that you're messing with the rounding modes. It's a compiler option rather than the pragma. But I'll worry about that not in this lecture today. But if you stop and think about it, there might need to be some way that you tell the compiler that you're going to start messing with the rounding mode, because when you do this could mess up, because the compiler, when it's compiling the code, it will make certain assumptions just to make the code more efficient. It will assume that you're not messing with the rounding modes unless you otherwise indicate it, because otherwise there are certain operations that are required to use certain rounding modes. Like, for example, when you convert from a floating point type to an integer type, the language standard specifies that this must be by truncation. So for example, the reason why the compiler might need to know about this sort of thing, if you start messing with the rounding modes, if you have a line in your code where you're converting from a floating point type to an integral type, the compiler might just say, well, I know before the compiler set the rounding mode up here to be round towards 0. So I don't need to change it in order to make sure that you get the proper truncation effect when you do this conversion. But little does it know that somewhere in your code, you've gone and changed it since the time it last set it. So this is the kind of reason why typically either you have like a pragma like this, or some way to indicate to the compiler, hey, in this chunk of code, I'm messing with the rounding mode. So whatever you last set it to, compiler, it might not be what you expect it to be, because I'm also playing with these values. So this is the reason why you need some kind of mechanism like this. Again, sometimes it's accomplished through compiler options, sometimes through, in the ideal world, it would be through pragmas, but it seems like I think most compilers don't seem to support this pragma, at least the last time I looked. Anyway, I guess I better stop here for today. Any last questions?